Okay, Koya, do you understand about chapter 3? I don't really understand it.
Oh, you mean about the memory hierarchy and cache? Well, do you know what is memory?
No.
Well, memory is a high-speed temporary workspace where your computer stores data and instructions for currently running application. There are different levels to memory, which is called a memory hierarchy. Do you know about it?
No, I don't know.
Well, a memory hierarchy organizes computer storage from smallest and fastest to largest and slowest to balance speed, cost, and capacity. One of the fastest memory is the register. It's extremely fast, taking only nanoseconds and are very small. Well, cache design aspect refers to the specific choices architects make when building cache memory to optimize speed, efficiency, and heat rate. Since cache it sits between the CPU and memory, its design directly impacts system performance. It's basically the rules that decide where the data goes in the cache, what gets kicked out when the cache is full, and how new data is returned back to memory. And I want to focus about what gets kicked out when the cache is full. To do that, we have to use cache replacement policies. Do you understand for now?
Yes, so far I understand.
Well, cache replacement policies is a crucial cache design aspect that determines which data to discard when the cache is full to make room for new data. The goal is to maximize the heat rate finding data in the cache and minimize miss penalty, which is time to fetch from main memory. One of the common strategies it stands for is least recently used, which is also called LRU. It's a cache replacement algorithm that removes the item that was accessed least recently when new data needs to be loaded into full cache. It's a way for a cache, a small fast memory, to decide which item to throw out when it's full.
Oh. Koya, what's wrong with you?
I don't understand what parallel processing is.
Oh, as it happened, I quite understand about it. Do you want to me explain?
Yes, please.
Okay, parallel processing ni is about allow multiple tasks to be executed at the same time. It also improve system performance and efficiency. It's widely used in modern computer system. Okay, should we move?
Yes.
Okay. Multiple processor organization is a computer system that use two or more CPU that share access to the same main memory, which is RAM. Okay. The main objective is to increase execution speed. The second is improve fault tolerance, and the last one is manage application efficiently. They have two main type of multiprocessor, which is shared memory multiprocessor and distribute memory multiprocessor. Okay. So far, do you understand?
Yes.
Okay. They have four application of multiprocessor organization, which is SISD, single instruction single data, SIMD, single instruction multiple data. The third is multiple instruction single data, which is MISD, and the last one is multiple instruction multiple data, MIMD. Okay. So we move on to symmetric multiprocessor, which is we also call SMP. Okay. SMP is where a computer system in which multiple identical processors share the same main memory, and have equal access to input and output devices. So they have a lot of advantage, which is SMP can improve performance through a parallel task execution, and also allows resources sharing via shared memory and input-output. This also provides better reliability and fault tolerance if a processor fails. Okay, the last advantage is simplified programming using parallel libraries such as OpenMP and MPI. Okay, do you understand so far?
Yes.
Okay, we move on to multiple programming versus multiple processing. Okay. Multiple programming is only use one CPU, while multiple programming use multiple CPU. From other aspect, multiple programming execute tasks by rapid switching compared to multiprocessing. It execute tasks in parallel. The main goal of multiprogramming is to maximize CPU utilization, but for multiprocessing is to increase system performance. Okay. This is the last part in parallel processing, which is AMDA law. AMDA law is a formula used to predict the maximum speed up of a program when only part of it can be parallelized. The overall performance is limited by the part of the program that must run sequentially. Okay, this is a formula of AMDA law. Okay, you can see. Okay, show you the example. Okay, 80% is the part of the program that can be parallelized, and 20% the serial part that cannot be parallelized. And we need to change the 80%, 20% to 0.8 and 0.2. Okay, the number of processors we have 4. Okay. As you can see, we just replace the P to the serial part, which is 0.2, and P per N2 P2 we change to 0.8, and the N we change to the 4, which is the number of the processor.
Okay.
We just calculate all the thing, and we got it about 2.5, which is this is a maximum speed up. Yeah. Even with 4 processor, the maximum speed up is only 2.5 times, because the serial part is still limited performance. This show that optimizing serial section is very important. Okay, do you understand?
Yes, I understand perfectly.